Alright, let me introduce to you the identity matrix. We use the letter I, obviously, to represent an identity matrix, okay? An identity matrix is a matrix that looks like this, okay? Now, this here is what's called a leading diagonal. They only exist for square matrices. Remember I said the 99%? Yeah, because identities only exist for square matrices, okay? But this is what's called a leading diagonal. These are diagonals, but this is a leading one. It's the one with the most number of elements in it, okay? So an identity matrix is a square matrix where the leading diagonal is all 1 and it's 0 everywhere else, okay? So that's a 3 by 3 matrix, okay? That would be an identity matrix for a 2 by 2 matrix, okay? An n by n identity matrix looks like this. So you've got 1, 1, 1, and you've got ones all the way down that diagonal, you see, and you've got zeros everywhere else, okay? So 0, 0, 0. Basically, look, I'm just filling all those out with 0. So if you can imagine that, if that was a n by n matrix, okay, then that would be, you know, what the identity matrix looks like for that, okay? Now, just link it in with geometry a little bit, okay? A 3 by 3 matrix is used for when you've got 3 dimensions, so x, y, z coordinates, or I, j, k values for vectors, okay? A 2 by 2 matrix is for when you've got 2 dimensions, x and y coordinates only, okay? So it gets rather interesting when you start to have n dimensions, okay? 4 by 4 matrix, 5 by, because you can't draw 4 dimensions, can you? It's tricky enough drawing x, y, z axes, okay? If you think about those 3 planes, the x, y, the x, z, and so on planes, okay? How do you draw 4 dimensions, 5, n dimensions? You can't. So can you just see why matrices suddenly help us to work around that problem, okay? And that's just a big indication as to why matrices come up at university, okay, to help us beyond 3 dimensions, okay? Because in A-level maths and further maths, you never go beyond 3 dimensions with matrices, okay? But anyway, the identity matrix has got the property that when you multiply that by another matrix, say for argument a square matrix, okay, you get exactly the same answer, okay? So for matrix A, if you multiply that by the identity, you get the same as if you do the identity times matrix A, and you get matrix A. So with these, the order does not matter which way around you do it. I'm going to show you a simple example, okay? So in 2 by 2 form, multiply this by this. So looking at the rows and columns, so you've got 2 times 1, 1 times 0. So the first element is 2. And then you move to the next column, 2 times 0, 1 times 1, you get 1. And then here, next row, 3 times 1, 4 times 0, you get 3. And then last, you get 3 times 0, 4 times 1, 4. And can you see? You've ended up with 2, 1, 3, 4, 2, 1, 3, 4, exactly the same matrix, okay? If you swap the matrices around, do it if you want. If you did that first, times by that, you get the same answer, okay? These matrices are, you know, the exception to the rule where AB is not equal to BA, all right? Why is the identity matrix important, okay? Well, it's going to help us with inverse matrices, okay, which I'll show you in, I think, the next video coming up, okay? But before I do, I want to talk to you about scalar multiplication. Now, a scalar is exactly the same as the definition we use for vectors. Remember, scalar is just a number, a numerical value, okay? So, you know, what I'm saying is, suppose you've got a matrix like this, 2, 4, 6, 7, okay? If you want to multiply that by a scalar, 3, okay, it's rather simple, okay? You just do 3 times each one of these elements, okay? And so you do 3 times 2, 3 times 6, 3 times 4, and 3 times 7, okay? There you go. It's just that sometimes it's easier, you see, if you want to rewrite this by taking a common factor out. So you can look at those and think, oh, there's a common factor of 3 there. Why don't we just take that outside the matrix? Okay. So you find it's more often the case that the other way round, we look at a matrix like that and we rewrite it like this. Okay, just because it makes some calculations easier. Like suppose, you know, that was 2 million, 6 million, 4 million, 7 million. Well, because they're all multiples of a million, you just take the million outside, and then you just got the 2, 6, 4, 7. Okay, does that make sense? I'm hoping that makes sense. Okay, right, that's it. I think I'm going to be doing inverse matrices next.